Do you know what foam, sugar, cars, and crowds all have in common? All of these things display a property we call jamming. Jamming describes the process in which some fluids, through an increase in density, can become suddenly stiff and act like a solid. This can be commonly observed when forcing granular materials through a funnel, as this increases the packing fraction above a critical point where the material gets stuck, causing it to stop flowing and become stiff like a solid. Whether a material will jam or not is also influenced by other factors, like temperature and shear stress. In the early 1990s, German physicists created a model called the Nagol-Shrekenberg model that can simulate highway traffic in which cars are analogous to granular particles that jam at large enough densities. In this model, the road is broken up into cells, which contain at most one car, as seen by the boxes in the figure. Furthermore, time is discretized into time steps, which are determined by the time it takes for a car to travel approximately 10 car lengths at the speed limit. And every car is assumed to have an integer velocity. The model shows how interactions between nearby cars cause cars to slow down, as a procedure is implemented in each time step and is applied to all cars simultaneously. To visualize this, we use a traffic simulation. The viscosity depends on the stress, or in this case, the density of cars. We see that a certain density causes traffic jams to occur, defined by a sharp drop in velocity. The density of cars can be increased by decreasing the amount of lanes available. This would create a similar situation as forcing granular materials through a funnel. As you can see, this will in fact create a jam. Further increasing the density of cars will increase the size of the jam. One of the main differences between a granular jam and a traffic jam is that usually a traffic jam moves itself, as the cars at the front are able to escape. In this video, you can see that the location of the jam moves opposite the direction of motion of the cars. This movement is caused by the fact that there are no direct interparticle or intercar forces, as the cars tend not to touch each other in order to avoid a crash. As previously stated, the cars at the front of the jam can escape. This enables us to explain another aspect of traffic jams, the importance of acceleration. In this example, we can see that if cars accelerate quickly after slowing down, they move away quicker and therefore the traffic jam grows slower. Therefore, a decrease in acceleration causes the traffic jam to grow at a faster rate. The acceleration of cars in traffic can be compared to the temperature at which granular particles or non-Newtonian fluids jam. While traffic jams are similar to the jamming of granular particles, they do have some distinct characteristics. The most prominent distinction would be the direction of the particles. In traffic, cars are only able to travel in one direction of motion, and they are not able to move backwards, while this is obviously not the case for granular particles. Additionally, there is a phantom effect that describes the interaction between cars. Cars slow down as they approach other cars in order to avoid a crash. They also have more prominent acceleration and deceleration phases compared to granular particles.